Rex, what kind of an introduction would you like me to give? What do you want me to talk about? About physics, about myself, or what?
Well, maybe it's a little bit about yourself and like what do you like to do outside physics?
Well, maybe let me go back to my beginning. I grew up in Logan, Utah, and in a place where the snow was so deep that when the snowplows came along, they pushed the snow up to drifts that were 3 times higher than my father was tall. And so I wanted to be a snowplow driver. That was obviously the most powerful job in the world. But then when I was 8, much like your experience, I guess, with your mother, my mother took me to a lecture for teenagers, but that I could understand at 8, about the solar system, and I fell in love with the idea of the solar system. And so we did a little project to draw a model of the solar system, and the sun as a 4 feet circle on the sidewalk in front of our house. And then she showed me how to do a calculation to figure out where the planets would be and how big they would be. And the Earth was about 3 houses down the street. And Pluto, which was then a planet, was in the next town. It wasn't even in the town. And that's how I got interested. And I just became fascinated with astronomy and started doing projects on it. It sounds like it's a lot like what you've done. Uh,
Yeah.
so that's how I got started. I'm now 83, so I've had nearly a whole century of life looking at physics and enjoying physics. I became a professor at Caltech, and I enjoyed greatly working with many students over the years. And I retired from that work in 2009. So that was, I guess, before you were born.
Yeah.
And so I've since then been doing projects at the interface between physics and the arts. So the movie Interstellar was one project, and I recently published a book of my poetry and paintings by a close friend of mine, a great painter,
Mhm.
called The Warp Side of Our Universe. So I'm doing things of that sort. So so anyway, that's a little bit about me. Why don't you go ahead with your questions?
Okay. Hi, Professor Thorne. Thank you for being with me. So I think I would like to start by formally introducing myself. And then we'll go with the questions. Is this okay?
Yes, please.
Okay, great. So, um, before we begin, I just want to say, you're my first interview. I haven't interviewed anyone else before, and I'm doing it because I want to show kids they shouldn't be afraid to speak with, other great minds like you and to ask questions or challenge ideas. I also want to interview you because, you're one of my idols. You're one of the greatest physicists of all time, and I've read many of your books. I'm reading one now, actually. I'm reading Time Warps and Black Holes. And I've watched many of your lectures, and I really admire your work on LIGO and gravitational waves, and also black holes. Just to get know a little bit more about me, I'm Rex, and I'm 10 years old. I live in New York, and I go to a school called Avenues. I like to play chess and guitar. I speak Chinese, and I also know how to solve a Rubik's Cube. I really like to read. But on top of that, I love physics. I really like physics because it challenges you to think beyond your general understanding of the universe and, it makes you push the boundaries of the known world. Like, you have to think about these enigmatic problems and, find answers to these impossible equations. And I think it's just great to do these things and, learn about the universe that we live in and, atoms and stars and all these wonderful things. So I think it's just a great topic to learn about.
I
Um,
do too.
yeah. Um, so before we start with the questions, do you have any questions for me? Uh,
No. Let's just go ahead.
okay, great. So I'd like to start the interview by getting your thoughts on a few theories I have on my own. Is that okay?
Yes, please.
So my first theory is on dark matter. Now, dark matter is very, it's a very mysterious. Well, we don't even know what it is, but it's a very mysterious subject, and it doesn't interact with normal matter. And so there are many theories on what it could be, and my theory is that maybe it could be made of primordial black holes, which are microscopic black holes that were formed in the early stages of the universe, where there were pockets of matter that, and if they became, too dense, they would easily form a black hole. And so maybe that's why, there's the gravity can hold the galaxies together is because they're made of black holes, which have an immense amount of gravity. Um, and maybe that's why it doesn't interact with normal matter because the black holes, the only thing that can escape from a black hole is Hawking radiation. What do you think about that?
So that is an idea that other people have also had, and and so there has been a lot of effort for by my colleagues, not by me, to try to see uh, whether they could find evidence for this or evidence against this. And so a lot of different observations have been brought to bear on this. The person who has been most active in this, well, suddenly, oh boy, I forget his name. Uh, it, it'll come to me. Anyway, because I haven't been working in this area. But I can send to you some references that you can look at to see what constraints, what limitations people have placed on this idea. I remember his name now. It's Bernard Carr. Bernard Carr was a student of Stephen Hawking's. He is works in England, and he's done a lot. He is the person more than anyone else who has really thought about your idea, and he and his and so what I recommend is that you go in and see what he has to say about it, because he really is the world's best expert on that particular idea.
Okay, yeah, I'll definitely do that. Uh, so my so on the subject of black holes, my second theory is on supermassive black holes.
Mhm.
Now, if you think about it, some of these black holes are so massive that if you take the timeline of the universe on how old it is, it seems really short, right? Because in order for these black holes to get to the size they are now, they have to, consume at least one solar mass every 4.5 months, if not more, right? But, that's not possible. Usually it would be every decade, if not, more. So maybe the supermassive black holes got a head start and they already started off with tens of thousands of solar masses um, because they formed inside quasi stars. Do you know what quasi stars are?
Yeah. Mhm.
Yeah, so maybe they formed inside them and then they just slowly consumed them and they just got a head start of, tens of thousands of solar masses and they can grow pretty quickly because of the environment that they're in and the early dense universe.
Yeah. No, that's a very interesting idea. And it is uh, so a colleague of mine named Martin Rees has for many decades has speculated about all the different ways that big black holes could have formed. And this is one of the pathways that he also has talked about. Um, and the and the physics of this is really quite interesting. If you have a black hole inside of some giant star, the physics of how the black hole eats the star from the inside out and how fast it can go or how much it's limited is a really interesting issue. We asked physicists to do calculations to try to model this. Sometimes calculations with pencil and paper, sometimes calculations with uh, computer calculations, writing programs to try to solve the equations for the flow of gas from the interior of a star onto a black hole. And and so, but for this particular topic, I think the person I recommend you go search on the internet for information about it is probably Martin Rees, who's also in England. In fact, these are both your friends of mine that I got acquainted with when I visited England.
Yeah, okay. So I think we'll definitely do that. I think it's a really interesting topic. So now I think we can now move on to the questions.
Hmm.
So now before we just start, I just want to say thank you for your work with gravitational waves and LIGO. It's really amazing, and I think your discovery can change, you know, the future of physics, and I think it will help us learn a lot more about the universe. And so I just want to say thank you for that. Um, so
Well, what you really need to do is thank the 1,000 people I worked with. It's LIGO was a big project. It was so complicated to do this, to build an instrument that could see these gravitational waves. There were so many things that could go wrong. And you had to build an instrument that dealt with all the things that could go wrong, that it took 1,000 people to pull it off. And I'm a sort of an icon for this project, but it's really the people, yeah, almost all of them much younger than I am, who really made it happen successfully. I get credit because I was one of the people who started the project, but I'm not one of the people who really made it happen in the end. It was people much younger than me in the next generation.
oh, okay. Um, yeah, well, just I think LIGO's really a great project, honestly. Maybe, maybe the if there'll be a future version of LIGO, yeah, Lisa maybe or another projects that can be launched.
Yes,
I
yes.
think it's really great. So, I think for our first question, we'll topic of gravitational waves. Do you think that gravitational waves can be used to send messages across space or help us travel in a new way?
They can certainly be used to send messages across space. They, uh, but they are so difficult to detect that only a very advanced civilization would be able to do this. We don't have the technology yet to be able to generate the waves that would be strong enough to be detectable by anyone far away. But you can see that, yes, a very advanced civilization could do it. And the one advantage of the gravitational waves is they're more penetrating than anything else. So if there's a lot of hot or dense matter between you and the place you're trying to communicate with, gravitational waves will be much more effective than anything else in passing through there and getting to their destination.
Okay, yeah, yeah, yeah. I mean, because well, gravitational waves are not really an object, more of the warping of space-time.
Yeah.
Um, so, do you think that maybe they could help us find wormholes if they do exist? Maybe like by going through them or around them and gaining a signature that's identifiable only to wormholes?
Well, so have you seen the movie Interstellar?
Yes.
Yeah. So uh, in the screenplay that was originally written by Jonah Nolan, the brother of Christopher Nolan, who was the director of the movie, in his drafts of the screenplay, the gravitational waves a wormhole out near Saturn was discovered from Earth because gravitational waves went through the wormhole and came to Earth. And astronomers on Earth in LIGO studied those gravitational waves and saw they were coming from near Saturn, which didn't make much sense. And as Saturn moved around its orbit around the sun, they kept coming from near Saturn. And that made even less sense. And the only way they could explain that was that the gravitational waves came through the wormhole in the wormhole's mouth uh, that they came out of was in orbit around Saturn. And so that was a story. That was science fiction, but that was the nature of the movie originally. Christopher Nolan got rid of that part of the movie. when, when he became our director. Jonah Nolan wrote his screenplays for Steven Spielberg, and Spielberg was the original director of the movie. And Spielberg dropped out, and Jonah's brother, Christopher Nolan, took over as director. And Christopher Nolan had a lot of additional science he wanted to put in. He said, we have too much science in here already to allow me to put more science in. It's going to overwhelm people. And so we'll remove the gravitational waves as a way of discovering the wormhole uh, in order to make room for some other things. He regretted it a lot after we discovered gravitational waves. We discovered gravitational waves in LIGO a year later. But anyway,
Wow.
that's just a bit of history uh, to give you an answer that yes, it's in principle possible. I think not likely, but it's impossible that you could use the gravitational waves to find wormholes.
Okay, now, yeah, I think it definitely makes sense that yeah, I think that yeah. Um I think maybe we can gravitational waves can help us if it is a wormhole, like, they can help us identify it. But I think they're also just very useful to have if, to because if, it doesn't matter really. Well, it does matter, but what you're detecting is the gravitational waves can go through anything except for black holes. So I think it's really, I think it's really going to be if we do, I think we'll know if we found a wormhole. I think we will know, especially if it's through gravitational waves. So, and speaking of detecting gravitational waves, what do you think the biggest difference is between gravitational waves emitted during the ring down phase of a black hole merger than than the gravitational waves emitted during that merger itself or right before?
The waves during the ring down phase uh, uh, look, they oscillate with a dying amplitude and a nearly fixed frequency. But the waves during the merger have changing frequency. They have an amplitude that goes up and then starts to come back down. And so, and we know these things from computer simulations, from solving Einstein's equations of relativity for what happens when black holes collide and when they merge. And so they we call this the waveform. The the gravitational waves stretch and squeeze space, and they stretch and squeeze then our gravity wave detectors, which is how we detect them. And so you just draw a diagram where you plot this amount of stretching up and then squeezing down, and that up and the gravitational wave then you see is a curve that we call the waveform. And the waveforms then describe how the stretching and squeezing changes with time. And it is these waveforms that we compute from mostly from computer simulations. To some extent, we can calculate with parts of them with pencil and paper, but mostly we need computer simulations. And the waveforms predicted are very different during the merger and during the ring down.
Oh, and oh, okay. So have we detected any like waves from both or the ring down or just the merger?
Oh, well, it's quite interesting. The first uh, gravitational waves we saw back in 2015, those gravitational waves, uh, they we saw the merger waves, but the LIGO team that did the data analysis was not able to find clear evidence of the ring down waves. And uh, however, experts in the computer simulations uh, went in. It's what's called the SXS team, a team that simulates extreme space times. It's a Caltech Cornell collaboration. And they went in and did many, many computer simulations to understand in great detail the predictions of general relativity. And they can compute those predictions to just as high an accuracy anyone might want using very sophisticated computer codes. And the SXS team concluded, in fact, after they'd done many simulations, then compared with the gravitational waves that were seen in that very first collision, they gave very convincing evidence that they all of the all of the waveform from the moment when the waves reached their greatest strength on afterwards was a superposition of just two modes of vibration of the final black hole. And using that, they have been able to do tests of general relativity based on the observations and compared with the computer simulations. So the bottom line is, just as of the last several years, uh, this has been done definitively, that we now really do see in that very first big signal from 2015, we see both the ring down waves and the collision waves.
Okay. Well, that's great then. Um, so um so I think that can definitely help us learn a lot more about especially about black hole collisions. And maybe it can not only help with black hole collisions, but maybe do you think if we detect gravitational waves, if it's possible from the Big Bang, what do you think we might discover if about how the universe began, or if we will discover things that we haven't learned already?
Those are the waves that I would most like to see, because the beginning of the universe was controlled, we are quite sure, by laws of physics that we call the laws of quantum gravity. These are laws in which both quantum effects that we usually just see down in atoms and molecules, things very small, and relativity effects, which you see in things really big, like black holes and black holes colliding. The quantum effects and the relativity effects come together, and they're both very important, in some sense, equally important in the birth of the universe. And we don't understand for sure how they get combined into a combined set of physical laws called laws of quantum gravity. So if we can see the gravitational waves from the Big Bang, uh, then that could help us to understand not just the beginning of the universe, but also the laws of quantum gravity that controlled the beginning of the universe. So that would be tremendously exciting. So I'm very eager to see those waves.
Yeah, maybe we'll see that when maybe after or before Lisa is built and other gravitational waves. Hopefully, we will. Um, so
Let me just say, I think in the end, it's going to be important to see those waves in several different ways with several different kinds of instruments. It's when you have a radically new discovery, unless the signal is really strong and really completely convincing, uh, you can sometimes be fooled. And so it's really valuable to have several different independent measurements. And I think we are likely, by the time you're in the middle of a career as an adult, as a physicist or whatever you choose to be, it's quite likely that we will be seeing those gravitational waves in at least two different ways with two different kinds of instruments. And I think that may be crucial in helping us sort out what's going on.
right, yeah, that will probably give us a lot of information from the Big Bang. Now, uh, the recent discoveries of the quasi-periodic eruptions, QPEs. Uh, what do you think about them? Or what do you think about the recent ones that were discovered from a dormant black hole that recently so-called awoken?
I don't know enough about it to comment. It's one of these things that I don't keep up as well as I should on very recent observations because I'm off doing other things. And another thing about me is I'm a little different than some of my colleagues who are willing to talk about things they don't know a lot about. I'm not willing to. I don't know enough uh, to really make comments about it. So you tell me, you tell me what you've learned about it.
Well, so the black hole, the quasi-periodic eruptions are basically they're X-ray bursts from the supermassive black holes that either consumed uh, pieces of matter really fast, or they interacted with the accretion disk, such that maybe they made a sudden move towards the another another black hole, or they you know the accretion disk grew larger. And so the quasi-periodic eruptions happen every 4.5 days or so. And we they're just X-rays, but we haven't yet figured out what they can tell us, but we're hoping that they'll maybe give us some valuable information about the black hole's accretion disk and other things like about the way the black hole might have consumed the matter.
So these are the quasi-periodic uh, uh, oscillations that you see from one particular source.
Yes. Yeah. So yeah, and this was actually, I think, 5 days ago, so it was really recent, or 7 days ago, so really, yeah, really recent.
I've been paying too much attention to other things. So it's good that you follow what goes on. I have found, let me just make the remark that it's useful to sort of keep track of what's going on, not just in physics, but in other areas of science. And a wonderful way to do that is through this little tiny little magazine called Science News. Uh,
Yes.
are you familiar with that?
No, but I'll check it out. I'll check it out after.
And I think it's
Let me write
really
that, let me write that down really quick. Science
Science News.
news.
Probably some online version of it. I have subscribed to it for decades, and
Wow.
it has little articles about exciting new observations or experiments in biology and chemistry and physics and artificial intelligence and all areas of science. And it's a marvelous way just to keep up with what's going on in the world of science.
Yeah, yeah. I've started reading a little more in like, just articles. So yeah, that's actually where I got the quasi-periodic eruptions. It's called Nature Astronomy.
Yes, nature
Yeah,
astronomy.
that one, yeah.
Science news is less technical than nature astronomy, but that's good in the sense that if you're really interested in physics, but you want to know what's going on in biology, Science News is a great place. You don't have to have as much of a background into biology as you would if you're trying to read a nature biology. But if you're, and so anyway, that's my recommendation for keeping up in other areas of things beyond physics.
Yeah. I really like reading, and then like, you know, I'd say probably engineering, my second favorite subject or third favorite. So I really like it. So Uh, what was it? Is it okay if I ask some like questions on your career as like a physicist?
Mhm. Please go ahead.
So, what was it like working with the legendary Professor Stephen Hawking? Like, did you guys have any debates, or any discoveries or concerns?
So this is an unusual thing. Stephen Hawking and I were very close personal friends. We never collaborated together on research. We only, for one brief period, worked on the same thing at the same time. And that was whether or not it's possible to build a time machine to go backward in time. And that was where we did have debates and we went back and forth and finally reached a common conclusion. But otherwise, I was working on gravitational waves while he was working on quantum aspects of black holes, for example. And so, but when we would get together, we would talk about life and love and death and things like that, which a little different than most physicist colleagues who get together and talk intensely about science.
Yeah. Oh, that's great. Well, um, I think it's great to have just a friend in physics, and hang out with them, and it's not always needed if you wanted to discover. I think that's great that you guys were just friends.
Mm. Yeah. No, it was wonderful.
Um, well, um, what was it like when you were a kid, 8 years old? What did you want to be a professor? Like when you were still young, like me, did you want to be a professor at Caltech, or did you want to be like a quantum physicist or some other area of physics?
Well, after I gave up snowplow driving for astronomy, uh, I really just wanted to understand astronomy and understand the solar system. And I imagined maybe I would be an astronomer. But I had an unusual family background. My father was a professor. My mother had a PhD in economics, but she was not allowed to work at the university because there were laws called nepotism laws that said that if a man had a job at the university, then his wife could not have a job there. And it and so she instead became a community activist and uh, worked in politics and trying to make life better for migrant workers and things like that. And so it was a but with a father that was a professor, a grandfather that was a professor, I I mean I knew as a child what the nature of professorial life was like. I I don't think I thought particularly whether I would become a professor, but did understand I wanted to understand the universe. And then when I was at age 13, I read a book uh, whose title was 1, 2, 3 Infinity by a cosmologist named George Gamow. And it was about uh, cosmology, about the origin of the universe. It had stuff uh, related to what we now call black holes in it. It was in curved space time. Um, but the important thing that I saw in there was that there are these laws of physics which control the universe. And since I was interested in the universe, the idea that you had laws of physics that controlled how it behaved and probably controlled how it was born, this was so exciting to me. I decided that that's what I really wanted to focus on. And so my focus turned from astronomy to physics and to the fundamental laws when I was 13.
Oh, that's great. Yeah. I think, we all sometimes it's I think for me it was I got inspired by a video on space, and I was amazed, and I just started learning about it. And I think it's great to learn about it. Um um so what is your advice then for a kid like me that wants to be a physicist like you someday?
I think it's remain curious, dig into things to try to understand them, uh, recognize that underlying what you learn in the books that you read, the magazine articles that you read, the things you see online, what underlies them is a lot of hard work on research that involves a huge range of tools, that involves experimental work, building experiments like LIGO. It involves work with telescopes that other people have already built. It involves computer simulations. It involves it involves paper and pencil theoretical work. Uh, it involves a huge wide range of different kinds of physics. And that means that there are a huge number of different ways that when you grow up, you can contribute, and a huge number of different directions you can go and still do really interesting stuff. But to do really interesting and important stuff requires a lot of hard work. And if you don't love what you're doing, then that hard work is going to become drudgery and you probably can't really do it very well. Uh,
Yeah,
it's
that
crucial.
I think that's happened before.
It's crucial that you love what you're doing. And so it was my grandfather when I was 4 who was also a professor, but he was a professor of business. But he told me when I was 4 years old, if when you grow up, you find a job that's like play, you'll be a big success. And I later came to understand what he really meant was if it's like play, if you enjoy it tremendously, then you'll work really hard. You'll so enjoy it, you'll just keep working so hard that you'll have great success.
You'll be motivated.
Motivated by the joy of it, by the thrill of it.
Yeah, I think physics is that kind of it's that kind of topic,
And for
honestly.
you, if and I have also found that I can find fun things in almost any direction I turn if I dig into them. But it's it has been very important in my career also that the things I focus on are things that I really enjoy doing. That's why at age 84, I'm still working as hard as I ever did because I'm
Mhm.
having enormous fun.
Yeah, physics is it's really fun, I think. Uh, well, um, we have 5 minutes. Uh, do you wanna I have an extra question if you wanna do you want
Yes.
me to ask? Okay, great. So, this is just a fun question. What is your all-time favorite subject in physics? Like just object, theory, anything.
Boy, I don't know. I have to think about that. I uh, right now that changes over time. Right now, my favorite subject is what are called vacuum fluctuations, which is probably not something you've heard of or even read about.
I've heard of it, but I haven't really got deep into it. But yeah,
So if you take a box and you remove from that box everything that you can remove from the box, you're still left with fluctuations of everything that could have been inside the box, fluctuating in and out of existence due to quantum mechanics, which has these uncertainties. You, it says that if you knew for sure there was nothing in there, then then the things that you knew were not in there will be flashing into existence very fast. Things, if something is absolutely known in terms of its existence, then its rate of change will be enormous. And so you wind up necessarily with fluctuations. These vacuum fluctuations are voracious. If they find any place they can suck energy out of something, they'll suck energy out of that and turn themselves into real matter, real particles. And uh, and so my most exciting and most interesting aspect of physics that I've been enjoying thinking about and writing poetry about, and my friend has been doing paintings about, is how these fluctuations uh, eat energy from the birth of the universe to create all the matter we see in the universe today, how they eat energy from a newly created time machine to destroy the time and make an explosion that destroys the time machine. And there are many, many other places where these things are they're going on. And how how we as humans can use these fluctuations to control uh, very high precision instruments, 21st century technology. So I if here that's a topic worth going and reading a little bit about is vacuum fluctuations and what they can do both in technology and in cosmology.
Okay.
That's my certainly today it's the thing that I'm having the most fun with.
Yeah. And they were how are they discovered and were they
It was a guy named. So we've known that we've known they should exist from just work in theoretical physics when the laws of quantum mechanics were developed in the 1920s. But that they had all that they could do all these amazing things was first pointed out, as far as I'm aware, the first physicist to understand this was a guy named Yakov Borisovich Zeldovich, was a Russian physicist. He was one of the two inventors of the Russian hydrogen bomb.
Oh
So
wow.
this terrible bomb that was invented in the United States by Edward Teller and Stanislaw Ulam. It was invented in Russia just a few months later, independently by uh, Zeldovich and Andrei Sakharov. Anyway, Zeldovich became a close personal friend and a mentor to me. And when I was in my young career, and I took Stephen Hawking to Moscow in 1972. And Zeldovich uh, called our attention to vacuum fluctuations and to what they could do, the amazing things they could do. And that triggered Hawking to do all his work during his whole career on
Okay.
Hawking radiation, on effects of quantum mechanics in the birth of the universe, on the nature of the universe's birth. It was all triggered by this guy Zeldovich, who was just brilliant and creative. He was a Jew, and there was huge anti-Semitism in Russia in that era, and so he he had to deal with that in his day-to-day life. Uh, but despite that, uh, 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 was he worked with Sakharov to invent the hydrogen bomb because they were scared to death that the United States had one. The United States would obliterate Russia in a war to prevent Russia from getting one. And it was a terrible time uh, that we went through in that period. And I saw it sort of firsthand, but as a young person, too young enough not to have been involved in that, and wound up knowing and doing work with these people who had done that kind of stuff. Anyway, so he is the source of the insights that I'm describing to you.
Yeah, that's great. I'll definitely I'll see maybe I'll do some research on that and
Read,
maybe I'll do a mini lesson on quantum fluctuations.
yeah. So I don't know how much you'll find out there in the. I hope you find a lot of stuff. I'm. Uh, I have been working on explaining these things through poetry and paintings with Leah Halloran, but
Yeah,
uh,
I think I
we
have that book.
we started doing it after we published that book, and so uh, you know,
Yeah, I have, in fact, actually right here, I have the two books with the one that I'm reading, and so I'm reading this one,
yeah, yeah, black
and
holes.
then this is the poetry one, right?
Yeah, that's the poetry one. Yeah, yeah,
Yeah, it's a pretty good book. It's pretty fun to read.
yeah, yeah,
Yeah, and so quantum fluctuation, or sorry, vacuum fluctuations
yeah,
they create Hawking radiation.
yeah. They do that by uh, they they sucked energy out of the expanding space when the black hole was being born long ago. And then they, having done that, they linger near the black hole and gradually leak out. As
That's a very interesting that's very interesting. Well, it's well, do you have any questions for me?
No, 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 I just encourage you to continue. You're obviously very enthusiastic and interested and understand well. And I think that you and other young people who have this love for science, whether it's physics or astronomy or biology or engineering, I strongly encourage you. I'm where I am because I was in your shoes a long, long time ago. And I've had a wonderful life as a result of following those interests onward over the decades.
Well, that's great. Well, I think it's been great meeting you, and it's been great talking with you. And thank you again just for giving me the honor of interviewing you. And we'd love the opportunity to meet with you again in the future in person, or, maybe attend one of your presentations someday or lectures.
Good. Well, I hope we get that chance. And thank you very much. I've enjoyed it greatly. Great
Thank you so
questions,
much.
great questions and great discussion. Thanks.